It is a pleasure to introduce our next speaker, Leslie Mavrakis from the University of Utah. The title of her talk is Combinatorial Characterizations and Branched Manifolds.
Great. Thank you very much for the organizers for inviting me, and thank you all for attending. So yeah, everything that I talk about today is going to be joint work with Daryl Cooper, who is my PhD advisor, and Priyam Patel. So I just want to kind of jump in and kind of give you, let me see if I can move this. Let's see. There we go. Give you what I mean by what a combinatorial characterization is. So of compact and manifolds is locally combinatorially defined, but that's kind of a mouthful. So what I'll say for the rest of the talk is LCD. If there exists finitely many simplicial balls, so we're going to call these models, and you should think about these as just like finitely many triangulations of an n ball. So I have some family of compact n manifolds, probably a very big family. It might not be finite, but I do have these like finitely many simplicial balls, and they have the property that a compact n manifold is in our family if and only if that manifold has a triangulation that locally looks like one of these models. So to say that a little bit more precisely, right, M has a triangulation so that every single vertex has a simplicial neighborhood that's simplically isomorphic to some model. So the idea is you have these finitely many models, they build everything in your family and they don't build anything else. And it's kind of that second part, they don't build anything else, that actually usually is the difficult part in proving that some family is an LCD set. Okay, so before maybe getting into why we might care about these things, I want to give you some examples. So if I take the set of closed hyperbolic surfaces, then every closed hyperbolic surface can be triangulated in some way so that every vertex has valence 7. And if I hand you some surface and you can put a triangulation on it so that every single vertex has valence 7, then actually you can show that that actually has to be a hyperbolic surface. Kind of in a similar way, the set of like closed Euclidean surfaces, so the torus, the Klein bottle, is an LCD set, and the model, it looks kind of exactly the same, except for your valence vertex has, the valence of your vertex, center vertex has valence 6. And then closed spherical surfaces also are LCD, and your center vertex has valence 5. So if I have some closed surface by its Euler characteristic, I can classify it as a hyperbolic Euclidean or a spherical surface. And so if I take the union of these 3 models, I can actually then show that the set of closed surfaces is an LCD set. So this kind of maybe raises a question, well, what families of manifolds are LCD? And just like in this example, it's actually true. If I take the union of 2 LCD sets, I will get an LCD set. But that's not obvious right now, because maybe I could take, right, models from one set and a model from another set and kind of put them together in some weird way, right, and build something new. So it's not clear right now why the union of 2 LCD sets is LCD, but it is true. And then the other thing is that oftentimes showing that a subset of an LCD set is LCD is difficult, and it might not be true. In particular, you have models that will build everything in the subset, surely, but right, it will build more. So the kind of the other direction showing that, right, you can't build anything else out of your models is the hard part. And so often proving that like a subset of an LCD set is LCD can be a harder question. So if you go about trying to like think what families of manifolds are LCD, that may be a hard question, but at the very least, it's probably a very tedious question, because not only do you need to, right, come up with the models, then the proof, you might have, many models. The proof can be very, very tedious. So this kind of motivates wanting a different perspective that doesn't have to deal with these like many models. And this second perspective that I want to introduce has to do with branched manifolds. So I will give the definition of what a branched manifold is, but before we do that, the rest of the talk will be in the piecewise linear category. So I kind of just want to do a crash course on PL topology. So we say that a cell is just the convex hull of finitely many points in some Rm. A polyhedron is just the union of finitely many cells. And then if I have two polyhedra and I have a map between them, we say that that map is piecewise linear if the graph of that map is a polyhedron. Now, this is like a very not intuitive definition at all. And I wanted to give you a concrete definition. It felt weird not to, but really your intuition of what a piecewise linear map is from, say, calculus is sufficient. So that's really what I want you to think of. But I did want to give a concrete definition. And then the point is a piecewise linear manifold is a polyhedron where every point has some neighborhood that's PL homeomorphic to the unit cube. And the key takeaway is that these things can be triangulated. Actually, every polyhedron is the underlying space for some simplicial complex. So if you want to go through the talk and just think about these as being simplicial complexes, that's fine. The idea is the PL manifold might have corners, but they have corners kind of in a nice way, so you can give these a triangulation. We're really going to use this triangulation going forward. Okay, so that's a crash course on PL topology. What is kind of the second perspective? So we have this perspective of a family of compact manifolds being LCD. What is the branched manifold perspective? So we say that a family of compact N manifolds is BM. So you should think BM for branched manifold. If there exists a compact PL branched N manifold, so I haven't told you what this is, but you should be thinking some compact piecewise linear topological space such that a compact N manifold was in our original family if and only if it properly immerses into the branched manifold. So I owe you these two definitions, what a branched manifold is, and what does it mean for a manifold to actually immerse into a branched manifold. But the takeaway right now is this perspective, right, means that there's like this compact, maybe topological space that acts as like a universal object for your family, right? And what we prove, and what I want to talk about more, is actually these perspectives are equivalent. So a family is LCD. So this information about a family of manifolds, like local combinatorial data, is equivalent to like this existence of this topological space. So this equivalence is actually somewhat surprising, why the combinatorics really is equivalent to having this like object. And so I do want to talk about why this equivalence is true, and that's kind of going to be the majority of the talk. But why we might care about any of these things is kind of the main goal of our project. So this is ongoing work. And so what we're trying to do is actually show that for each of the 8 Thurston geometries, the set of closed orientable 3 manifolds that admit that geometry is LCD. So Thurston showed that, right, a closed 3 manifold can kind of be decomposed into components where each component has one of these 8 geometries. And so we're trying to show that the set of closed 3 manifolds where they have entirely one of these geometries, that set is LCD for each geometry. So that's going to be for each geometry, either going through and finding, right, the models for that geometry, or for each geometry, and this is actually the technique we use for 7 out of the 8 geometries, building the branched manifold that kind of acts as the universal object for these. So the geometries, 6 of them are ciphered fibered spaces, and then you have sole geometry, and then of course you have the most complex, most interesting geometry, hyperbolic space. And so for everything but hyperbolic, how we go about this is building the branched manifold. And so we can actually draw a picture of the branched manifold, and I'll talk about the sole geometry case at the end of the talk. And that actually will hopefully be out on the archive pretty soon. the ciphered fibered cases were part of my thesis, and then hyperbolic is what we're working on next. And really the idea there is we're going to use this equivalence really nicely and build the thick part using models, build the thin part using branched manifolds, and use this equivalence, kind of merge it together. But that is ongoing work. So I won't talk too much about that. Okay. So that's kind of what we're trying to do. But I do kind of owe you these two definitions, right? What actually is a branched manifold? So branched manifolds were first introduced by Bob Williams in the 70s, and he used them to study dynamical systems. Bob Williams was working in the smooth category, so his definitions do differ from ours a little bit. And locally, in low dimensions, branched manifolds really show up a lot in literature. So in dimension 1, a branched manifold is a train track. And in dimension 2, a branched manifold is a branched surface. So here, because we're in a smooth category, every single point like kind of has a nice, well-defined tangent space, which is not going to be true in our case. So what's our definition? We say that a PL branched manifold is a pair, W and pi, where W is a compact polyhedron and pi is a collection of maps, which we call local projections. So these maps go from subpolyhedrons of our W to the unit cube, and they have some properties. So first, every single WI, so the domain of some local projection, is a connected polyhedron, and these interiors cover the whole branched manifold. The second condition, first, you need a definition. So first, the definition, we say that a sheet is a polyhedron D, subset of your WI, such that the restriction to D is a PL homeomorphism. And the point is that these WIs are a union of sheets. So I want to talk about this more in a second, but I just want to give you the last condition, which is some compatibility conditions. So you have these WIs and these maps on them, right? And you want to make sure that these play nicely in intersections. So there is some compatibility condition, but it doesn't really matter for the talk, and it's a little technical, so I left it out. So I really want to kind of talk about the sheets for a second. So what is kind of our local picture? These on the screen are kind of the local picture for Bob Williams in the smooth category, and our local picture is kind of just a PL-ified version of this. So here, here's my dimension 1 picture, and here's my dimension 2 picture. And so you can think about, in this case, really, they're drawn intuitively, where if this is some WI, right, if this is some WI, the map down to an interval is really the projection map, which is why we call these a local projection. So you can think about collapsing this train track. And then you ask yourselves, okay, well, what's the sheets? Well, we have a sheet here, and we have another sheet here. And in the same way, our dimension 2, if we have a local projection, right, that is really collapsing this picture, then we have 3 sheets. We have a sheet here, we have a sheet here, right, and we have a sheet here. Okay, and so we just want these, right, if I take the restriction to any of one of these sheets, I get a PL homeomorphism. Okay, so that is a branched manifold, and now I want to give you kind of an example of a branched manifold. So I'm going to take this definition and move it up. So as an example, well, if I take 2 compact surfaces, so say I have the genus 2 surface with a boundary component and genus 1 surface with a boundary component, and if I glue this using a homeomorphism, of course, I get the genus 3 surface like normal. But if instead I glue using a covering map, so say a ×2 map, then, right, I have 2 points on my left-hand side collapsing to 1. And if I take a little neighborhood of that and see what happens in the image, I get exactly this branch sheet structure. And so actually, if you take manifolds with boundary and you glue their boundaries using covering maps, you get a branched manifold. And this is how we build most of our branched manifolds, is you take manifold pieces and you glue their boundaries together using coverings. Okay, so that's what a branched manifold is. Now we can kind of talk about what it means for a manifold to actually immerse into it. So if I have some manifold and I have a PL map between the manifold and the branched manifold, we say that it's a PL immersion if the map is locally injective into sheets. So let's kind of see what that means. So if I take this picture again, right, where I have this like part of a train track that I'm collapsing using a projection map. So I have these two sheets. Well, in order for a map to be an immersion, I would, if I wanted to immerse some interval into it, right, my options is the interval could go like this because that's one sheet, or the immersion could go into, right, the other sheet. What can't happen is I can't backtrack like this. I can't immerse the interval into the train track in this way, right? Because then it's not locally injective into some sheet, right? This point, if this point's mapping right here, right, it doesn't have a neighborhood that injects completely into a sheet. And so while we don't have like this well-defined tangent space like Williams does, the sheet structure is really telling you what you can do in an immersion. And so the sheet structure is essential in the definition of the branched manifold, because you could put different sheet structures on your branch. You could take the same polyhedron and have a different set of local projections, and then things could immerse in different ways into the branched manifold. So a lot of the data that you get from having a well-defined tangent space in like the Williams perspective, we recover by having like these definitions of sheets. Okay, so that's a branched manifold and what it means to immerse into a branched manifold. And now I kind of want to give you an idea of why these ideas of an LCD set versus a branched manifold perspective are actually equivalent. So I'm just going to go through kind of a general idea of the proof and not get too nitty gritty into the details. So one direction is actually a lot easier than the other direction. If you're given a branched manifold and you want to find the set of models that kind of characterize that, this is the easier direction. Why? Well, what do? You first triangulate your branched manifold, and then you want to create your models. And so maybe the first idea of what your set of models could be is if I take some vertex and I take the smallest simplicial, like I have a triangulation of it, right? The smallest simplicial neighborhood of that vertex. Maybe that has branching, right? So what I could do is take that smallest neighborhood, we call that the star, and we could intersect it with the sheets. And that's going to give you a set of models which are all, right, homeomorphic to the ball, right? Okay, so what we do is then we need to ask, if you immerse into the branch manifold, is it modeled in this set? And the answer is yes, you can actually just like pull back the triangulation through the immersion. But the issue is, if you ask if N is modeled on this set, does it immerse into the branch manifold? And unfortunately, this set isn't quite right. The answer is not necessarily. And the issue is you can actually build more things in your model out of these models that don't actually immerse into the branched manifold. And that's because you actually kind of want more information. You want to know kind of what's next to the model. Where can your immersion go next? Like there's this, the model itself is not enough data. And so to address this problem, you kind of need to edit how these models can actually fit together. And we do this in kind of, this is the tedious part of the proof, but you do this by further subdividing your models using asymmetrical triangulations, which in some way control how these models fit together. So I don't want to go into that too much. The point is maybe your first idea of what the set of models should be almost works, and you just kind of need to have this fix that kind of makes sure that you can control how the models fit together. Okay, so that's the idea of one direction. How do you get models from a branched manifold? The other direction is actually the more difficult direction. So if I start with a set of models, right, how do I actually construct a branched manifold that has this property? And this is difficult because, one, you have all these models. It's hard to even think about how to put them together to get a branched manifold. And then you have to prove that this is a branched manifold and it has all the properties you want. Is kind of the main difficulty. So I want to at least show you how we kind of construct the branched manifold. So if we have some family of manifolds that are triangulated and they're modeled on this set, right? And they have the triangulation that you get the modeling from. And if I just take the union of this, so this is some, right, very large union, and right, a branched manifold needs to be compact. So that's kind of the issue here, is we have this union of many, many, many manifolds, right? And we need to make sure that we get something compact from it. And so if I put an equivalence relation on this set, so I'm going to take the vertices of this set Q, and I'm going to send them to some, and we'll show in a second that it's a finite set L, right? So L is just some finite set, and we're going to put a relation on it so that two vertices are sent to the same thing, right? If and only if they have large simplicity isomorphic neighborhoods. So this is vague on purpose, but the idea is these neighborhoods will at least contain the model, right? So these large simplicity neighborhoods contain a model because this thing is modeled on some set of models. And you can show that since all of these manifolds are modeled on the same set, you can do this using finitely many labels. So this L set is finite and it's the labeling set. And then you can define a quotient of Q, right? And you can say, okay, well, simplicities are going to be identified if and only if all of their vertex labels match. So I'm taking Q and I'm identifying pieces which look similar in a large neighborhood. And it turns out that then first, right, you need to show that this is a branched manifold. That takes work to show that you actually get all the structure of a branched manifold. And then you need to show if you're modeled on the set, then you immerse into the branched manifold. And then what turns out to be actually the hardest part is if you immerse into the branched manifold, then you're actually modeled on the set. And that's the hardest part because the immersion is a very small local condition, but right, these models could be quite large. And so that's kind of where the difficulty, and that's actually the hardest part of the whole paper is showing that when you immerse into this branched manifold, you're actually modeled on the original set of models. Okay, but hopefully you can at least see maybe how you get models from a branched manifold, how you might get a branched manifold into models. And that's kind of the main idea. So I want to just take a few minutes to kind of talk about the picture in soul geometry. So if you recall, right, we're trying to show that, at least in this case, right, the set of closed oriental three manifolds that have soul geometry is LCD. And so a closed three manifold has soul geometry if and only if it's a torus bundle with a Nosov monodromy. So that means it's torus times interval with one side glued to the other using an Anosov matrix. Or it's a semibundle, a soul semibundle. And that just means it has a twofold cover. That is a soul bundle. So I do want to just talk about this first case today because it's the easier case to see. So we'll star that. And so what's the point here, right? So we want to make sure that we can build some branched manifold so that every soul bundle immerses into it. And if you immerse into it, you are a soul bundle. So we show that actually you can kind of write all Anosov matrices. Well, a matrix is a Anosov if and only if it's conjugate into kind of this, it's a regular language using matrices. So what's the point? We have this L matrix, we have this S matrix, and then the idea is a matrix A is a Nosov if and only if it's conjugate into something that can be written where you start with S then you multiply by L, and then you can do LS or L any number of times. And then you can then build your branch manifold kind of using this language. So here's a one-dimensional picture. Oh, I should note that, okay, if you have matrices that are conjugate, then their torus bundles are homeomorphic. So this is kind of the one-dimensional picture for Sol. This is a train track picture, so it's one-dimensional, but it's representing a three-dimensional object. The idea is whenever you have a point here, that's actually going to be a torus in the branch 3 manifold. And when I have an interval with a label on it, or maybe a label with an arrow, what happens is I'm taking torus times interval, and I'm going to cut right at that point. And then I'm going to reglue in the direction of the arrow using the label. So I'm going to glue in this direction using the L matrix. And I can build my branch manifold in this way. And the point is there's these twos hanging out. These just prevent unwanted immersion. So if I just had an L right here, then the torus bundle with a monodromy L would immerse right into this part of the branch 3 manifold. And that has nil geometry, doesn't have Sol. So we kind of, just like in the beginning where you had this, when you glue using a covering map, you have branching. We force branching right here to ensure that you can't just immerse into this loop. And the idea is once you do that, you kind of need to undo it at some point. So we have this loop. So I don't want you to think too much about that. It's just preventing kind of a unwanted immersion. But the point is, if you have some word in this regular language, right, say SL, maybe L squared, that's going to tell you a path to go around in this train track.
You have almost 1 minute. Time is almost up.
Okay. I'll just say that, yeah. And so that will give you your immersion in the branch. So yeah, that is all I have to say. So we'll.
Thank you for the nice presentation. Let me stop the recording.